The National Electrical Code, specifically Section 250.32b2, addresses the grounding requirements for separate buildings or structures supplied by a feeder. This section outlines conditions under which the grounded conductor of the feeder can be connected to a grounding electrode system at the separate building. Understanding these conditions is crucial for ensuring electrical safety and code compliance. Condition 3 of 250.32b2 states that ground fault protection of equipment has not been installed on the common alternating current service. The key here is to understand what constitutes common ground fault protection. The National Electrical Code Handbook provides clarification on this matter. Ground fault circuit interrupter, or GFCI, protection is generally not considered common ground fault protection for the purposes of this rule. Common ground fault protection is typically located downstream of the point of common bonding. This point is where the grounding electrode conductor or the grounding electrode system connects to the grounded conductor. Examples of this include a grounding conductor bus in the service equipment, or the connection between a water pipe and the grounded conductor of a feeder or branch circuit. Therefore, individual GFCI circuit breakers installed in the main building's panel or any ground fault protection in the second building would not qualify as common ground fault protection. Consequently, if there is no common ground fault protection, a 4-wire feeder, including a separate equipment grounding conductor or EGC, would be required. This ensures a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. However, there is another scenario to consider. If the two buildings in question qualify as multiple buildings or structures supplied from a common service, as defined in 250.32 burn, then the requirements change. According to 250.32 burn, a 4-wire feeder is required in any case, regardless of whether ground fault protection is installed or not. This means that the feeder to the second building must have an equipment grounding conductor, or EG, even if ground fault protection is present. To summarize, firstly, if there is no common ground fault protection as defined by the National Electrical Code and the buildings do not qualify as multiple buildings supplied from a common service, a 4-wire feeder with a separate equipment grounding conductor is required. Secondly, if the buildings do qualify as multiple buildings supplied from a common service, a 4-wire feeder with an equipment grounding conductor is required regardless of the presence of ground fault protection. It is important to note that these requirements are based on the National Electrical Code and may vary depending on local amendments or interpretations. Always consult with a qualified electrical inspector or engineer to ensure compliance with all applicable codes and regulations. Failing to properly ground electrical systems can have serious consequences, including electrical shock, fire hazards, and equipment damage. Understanding the nuances of grounding requirements, such as those outlined in 250.32b2, is essential for safe and effective electrical installations. Remember that the equipment grounding conductor provides a low impedance path for fault current, which is crucial for the proper operation of overcurrent protective devices such as circuit breakers and fuses. When a ground fault occurs, the fault current flows through the equipment grounding conductor back to the source, causing the overcurrent protective device to trip and de-energize the circuit. This helps to prevent electrical shock and fire hazards. In the absence of a properly sized equipment grounding conductor, the fault current may not be high enough to trip the overcurrent protective device, resulting in a prolonged fault condition and increased risk of electrical hazards. Furthermore, the presence of ground fault protection, such as GFCI circuit breakers, adds an additional layer of safety. GFCI circuit breakers are designed to detect even small amounts of leakage current to ground, which can be indicative of a ground fault. When a GFCI detects a ground fault, it quickly trips the circuit, interrupting the flow of electricity and preventing electrical shock. However, as discussed earlier, GFCI protection is not considered common ground fault protection for the purposes of 250.32b2. Common ground fault protection typically involves more comprehensive systems that monitor the entire service or feeder for ground faults and provide coordinated tripping of overcurrent protective devices. These systems are often used in larger electrical installations, such as commercial or industrial facilities. In residential applications, individual GFCI circuit breakers are more common for providing localized ground fault protection in areas such as bathrooms, kitchens, and outdoor receptacles. When installing a feeder to a separate building or structure, it is crucial to carefully evaluate the grounding requirements based on the specific conditions and the applicable electrical codes. This includes determining whether common ground fault protection is present, whether the buildings qualify as multiple buildings supplied from a common service, and whether a 4-wire feeder with an equipment grounding conductor is required. If there is any doubt, it is always best to consult with a qualified electrical professional to ensure compliance and safety. The NEC also includes specific requirements for the size of the equipment grounding conductor, which are based on the size of the overcurrent protective device protecting the feeder. These requirements are outlined in Table 250.122 of the National Electrical Code. It is important to select an equipment grounding conductor that is large enough to safely carry the maximum available fault current without overheating or causing excessive voltage drop. In addition to the size of the equipment grounding conductor, the National Electrical Code also specifies the acceptable methods for installing and terminating the conductor. The equipment grounding conductor must be securely connected to the grounding electrode system at the separate building or structure, as well as to all metal enclosures and equipment along the feeder pathway. Proper installation and termination are essential for ensuring a low-impedance ground fault path and the effective operation of overcurrent protective devices. In summary, understanding the grounding requirements for separate buildings or structures supplied by a feeder is crucial for electrical safety and code compliance. Carefully evaluate the conditions, consult the National Electrical Code and other applicable standards, and seek guidance from a qualified electrical professional when necessary. By following these guidelines, you can help to ensure safe and reliable electrical installations that protect people and property from electrical hazards. The National Electrical Code is updated every 3 years, so it is important to stay current with the latest edition and any local amendments. These updates may include changes to the grounding requirements or clarifications of existing rules. By staying informed and continuously improving your knowledge of electrical codes and standards, you can contribute to a safer electrical environment for everyone. Also, be aware that there might be other sections in the National Electrical Code that apply to a particular situation. For example, Section 250.30 covers grounding electrode system requirements. This section details the types of grounding electrodes that are permitted, such as metal water pipes, concrete encased electrodes, and ground rings. It also specifies the requirements for bonding different types of grounding electrodes together to form a comprehensive grounding system. Section 250.66 provides guidance on sizing the grounding electrode conductor, which connects the grounding electrode system to the service equipment. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Ensuring that the grounding electrode conductor is properly sized is crucial for providing a low impedance path for fault current to flow back to the source. Another relevant section is 250.104, which addresses bonding of metal piping systems and exposed structural metal. Bonding these metal components to the grounding system helps to equalize their potential and prevent voltage differences that could create shock hazards. The National Electrical Code also includes specific requirements for surge protection devices, or SPDs. These devices are designed to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. Surge protection devices are typically installed at the service entrance and at downstream panels to provide comprehensive surge protection throughout the electrical system. When installing a surge protection device, it is important to follow the manufacturer's instructions and the requirements of the National Electrical Code. This includes properly grounding the surge protection device to ensure that it can effectively divert surge current to ground. In addition to the National Electrical Code, there may be other applicable standards and regulations that govern electrical installations. These may include local building codes, utility company requirements, and industry standards. It is important to be familiar with all applicable requirements and to ensure that electrical installations comply with all relevant standards. Finally, remember that electrical work can be dangerous if not performed properly. Always energize circuits before working on them and use appropriate safety equipment, such as insulated tools and personal protective equipment. If you are not qualified to perform electrical work, it is always best to hire a licensed electrical contractor to do the job. The principles of electrical grounding are based on fundamental physics. Grounding ensures that non-current carrying metal parts of an electrical system are at a 0-volt potential relative to the earth. This prevents dangerous voltage build-up that could cause electric shock if someone touches a faulty appliance or equipment. The equipment grounding conductor, or EC, plays a vital role in this process. It provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices like circuit breakers to quickly trip and disconnect the power. Without a proper EGC, fault currents could linger, creating a shock hazard and potentially leading to a fire. The grounding electrode system, which includes components like ground rods, metal water pipes, and concrete encased electrodes, provides a connection to the earth. This connection helps to stabilize the voltage of the electrical system and provides a path for dissipating fault currents. The size of the grounding electrode conductor, which connects the grounding electrode system to the electrical service, is determined by the size of the service entrance conductors. Ensuring that this conductor is properly sized is crucial for effective grounding. Bonding is another important aspect of electrical grounding. Bonding involves connecting all non-current carrying metal parts of an electrical system together to create a common electrical potential. This prevents voltage differences between different metal parts, which could create a shock hazard. Bonding is typically achieved by using bonding jumpers, which are conductors that connect metal enclosures, conduits, and other metal components. Ground fault circuit interrupters, or GFCIs, provide an additional layer of safety by detecting small leakage currents to ground. GFCIs are designed to quickly trip and disconnect the power when a ground fault is detected, preventing electric shock. GFCIs are commonly used in areas where there is a risk of moisture, such as bathrooms, kitchens, and outdoor locations. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning strikes or other transient events. SPD diverts surge currents to ground, preventing them from damaging sensitive electronic components. SPD are typically installed at the service entrance and downstream panels to provide comprehensive surge protection. Electrical codes and standards, such as the National Electrical Code, provide detailed requirements for electrical grounding. These codes and standards are developed by experts in the electrical industry and are designed to ensure the safety of electrical installations. It is important to be familiar with the applicable codes and standards and to follow them carefully when performing electrical work. Proper electrical grounding is essential for the safety of people and property. By understanding the principles of electrical grounding and following the applicable codes and standards, you can help to prevent electric shock, fire hazards, and equipment damage. Electrical safety should always be a top priority. If you are not qualified to perform electrical work, it is always best to hire a licensed electrical contractor to do the job.